Hello, everyone. Welcome to our session. Thank you for attending. So, today we'll be discussing a case that we had personally worked on using OpenSearch with OpenTelemetry to solve real world scenarios. So, I'm Abhay and this is Shambhavi. We are thrilled to be here at our first OpenSearch Con, and today we'll share a story about solving a very real, very painful operational problem that we faced using two very powerful tools, OpenTelemetry and OpenSearch. You're going to hear about the technical pieces, but more importantly, you're going to hear about the whys, the hows, and the lessons that we learned along the way. And by the end, you'll hopefully leave with some ideas that you can take back to your own systems and that can maybe help you in your day to day life. All right, a little bit about us. I'm Abhay, and I've been in tech for about 5 years now. And I currently work in Atlassian as a software developer. I primarily work on backend systems, and my personal experience with OpenSearch has mostly been around observability more than the search aspect of it. Also, I have with me today Shambhavi Sarin, who's working as a software engineer in Salesforce, and that's a little bit about us. So let's move on. Let's lay some groundwork first. OpenTelemetry and OpenSearch are large systems, and if you're new to them, it can be a little overwhelming. So let's start simple and do a reset. OpenTelemetry, also called OTel, is an open source project that provides libraries, APIs, and agents to collect telemetry data. Now, telemetry data includes traces, metrics, and logs. So if you're building distributed systems, multiple services that talk to each other over APIs and gRPC, what have you, telemetry gives you visibility into what's happening across the board end to end. The main key idea amongst all this is context or trace propagation. Now imagine you call an API, that API calls another service, that one calls another, and so on. This is how it goes. So you want to track that whole chain down, right? OpenTelemetry quietly follows this journey by creating a trace ID, or also sometimes referred to as context. And this includes multiple spans, what we call spans, for every step taken along the way. So when service A calls service B, OTel automatically passes the tracing info in the request headers or the metadata in gRPC. And each service adds its piece of the story and the time it took or any errors it faced, like so what we are discussing here will be the system of a food delivery company, an e-commerce food delivery company. So in that context, each service will add its piece of the story, like I validated the order, I charged the card, I scheduled delivery, and all of these will be recorded as individual spans. Later, we will combine all these spans to form a full trace, a clear map showing every step the order took, where it was fast, where it was really slow, or if it faced any errors, or if any of the services failed in the middle, and why so. This is how we can debug complex issues across services quickly without any guesswork involved as to where and what broke. But collecting data from services is only half the story. Once you have all of these things, you have your logs, you have your metrics, you have your traces, you need a way to manage and process them. You need to send that data to your observability tools. You don't want every service individually handling that. That's messy. It's also fragile and prone to break. That's exactly where the OTel collector comes in. The OTel collector is like a middleman between your applications and your observability backend. So instead of sending data directly to a backend like OpenSearch, you send it to the collector first. So so what we did is you can spin up your collector like a gateway, and all of your services will send it to the gateway, and it will collect them. So that is how we configured our OTel collector. So what it does, it's three things. First one is that it receives data from your service. The second is that it processes or transforms it, and anything like that you want, filtering, batching, enriching. Then the third part, it pushes it out, exports it to whatever you want. In our case, OpenSearch. This gives you flexibility. You can change backends later without touching your application code. You can reduce load on your systems by batching and compressing data. You can also do things like sampling, where you only send some important traces and don't do the whole thing. So the OTel collector is like kind of a router / delivery agent for your logs. Now, once OTel collects your logs, you need a place to store, search, and analyze them. This is where OpenSearch comes in. Sorry, it's open source, highly scalable, and gives you the flexibility to handle massive volumes of data. But I'm sure everyone knows that here. But yeah, so with OpenSearch and this hotel in combo, we can search billions of logs in seconds. We can build dashboards. We can set up alerts. It's a game changer. All right, moving on to the next part. How do we get logs from OTel into OpenSearch? So this is where Data Prepper comes in. Data Prepper is a component that takes in raw logs from OpenTelemetry in our case, and processes and enriches them if needed, and then puts them into OpenSearch. Think of it like a bridge that cleans, parses, and structures your data so that OpenSearch can store and query them efficiently. When we say Data Prepper processes telemetry data, it actually works through something called a pipeline. A pipeline in Data Prepper has three things, three key parts, you may say. A pipeline source. This is where how Data Prepper receives the data. Common sources can be hotel collector in our case, or HTTP endpoints, a Kafka, or SQS topics. So your service can emit traces, the hotel collector collects them, pipeline source receives them. The source here is hotel collector. The second part is a processor. So what happens to the data inside Data Prepper, inside the pipeline? These are the steps that transform or modify the data. You can have multiple processors also chained together if you want to do multiple things. Like the major ones are like trace raw processor. It takes incoming raw trace data, which has spans, converts it into trace groups, and links spans together into a full trace. You have a drop processor, which can remove unwanted data, example, a log level that you don't want. Then we have enrich processor, which adds extra information, any other metadata you might need, like region, environment tags, whatever. And we have grok processor, which parses unstructured text logs into structured fields. So basically, all of these processors do one thing. They transform and enrich your data in multiple ways. Whichever way you want, you can do that. The third is a pipeline sink, where data goes out. This is where the processed data is sent after transformation. Common sinks are S3 and what we use in our case on OpenSearch, and you can use other storage systems as well. So after traces are processed, organized, sync pushes them into OpenSearch, ready for dashboards and queries. So sync is essentially the exit point of Data Prepper. Now, once your data is in OpenSearch, you can use OpenSearch dashboards to visualize it. What are OpenSearch dashboards? We'll do a small context set. Once all your logs, traces, and metrics are collected and stored in OpenSearch, you need a way to actually see and analyze that data. This is where dashboards come in. You can search through your logs, visualize your data using charts, graphs, and maps, build dashboards, and set up alerts. Now, in the context of a food delivery provider, what could we do with OpenSearch is what we thought in the beginning. So what we did was create dashboards that show API failures, order delays, server errors. So order delays is an important metric if you're trying to deliver on time. Then we use filters and queries to find specific logs, like show me all the orders that failed in the payment service. So for example, if you have an outage in the payment service, you want to see how many payments in the last hour went through, how many failed. So there's something we would use to find them and take necessary action to remediate that. Then we have visualizations, which are basically charts or plots for important stuff like order throughput, how many orders do we get every month, minute, second, whatever. Average delivery time, it needs to be quick, and mean cost of delivery of packaging, stuff like that. So these graphs help us keep track of the trends as they move and grow and decline. This also helps us reduce incident response times. So it helps the on-call see where exactly the problem lies, if the latency is going through the roof, if any CPU is spiking, stuff like that. So this also helped us with that, as you'll see. Now I'm going to hand it over to Shambhavi to get into the problem statement.
Hi everyone. Okay, so let's dive into the problem statement. Today I'm going to walk you through a real world scenario where we used OpenTelemetry along with OpenSearch to solve a critical observability problem in a food delivery company that we worked for. We'll show you how we tackled the issues like debugging delays, tracing failed orders across microservices, and reduced on-call resolution time, all by building a powerful end-to-end telemetry pipeline. Okay, so let's talk about the problem we faced. So to begin with, I'll walk you through the food delivery app that we're referring to. This app, think of it as the one stop for any food and grocery needs that a user needs. And so let's begin with how a typical food order moves through the system behind the scenes. When the user opens the app, they land on, you can refer to that as a home page. This is the page that allows them to select what they want to order from. Like they want to order from a restaurant, they want to fulfill some grocery needs. So based on that, the next. So let's assume for the purpose of our example that they want to order food from a restaurant. Now, once they pick the restaurant and they browse through the list of restaurants that they want to order from, they pick a restaurant and choose one. That's when they land on what we call as the menu page. You can also land on this page if you have the link directly to this restaurant on the app. This is the page that will show you the list of items being sold by the restaurant along with their prices for individual items, any add-ons you want to add, and so on. This page will allow the user to add the items to their cart and check out further. Once the items are added to the cart, the user can navigate to the cart page where they can see all the items that are listed. The cart page will also display your item total, any additional taxes and charges, any delivery fees or pricing that might be applicable. There will be a subtotal that will sum up all the line items in this cart. Now, if the user is satisfied, they can go ahead and make the payment. This is what we'll call as the payments page or the payment gateway. And post this, they'll be navigated to a page where they can track their estimated delivery time of the order and other updates. This might sound simple, but in reality, it involves 20 plus microservices, each with their own database, API, and their own observability system. So let's dig deeper and understand some of the code terminologies. We'll go into what a request ID and what an order ID is and how they will differ from each other in this scenario. So for a food delivery platform, every time a customer lands on a page like a home page, menu, or any other, the request ID is generated if it is not already present. The system needs a way to uniquely identify a request as it moves through multiple services across the system. So the unique identifier for this will be the request ID. Now, every time a customer places an order, that is when an order ID gets generated. The system will use this as the unique ID to identify any order that moves through the multiple steps further. And this is what we'll refer to as the order ID. So a simple difference between them is that request ID is generated irrespective of whether the order is placed or the payment is made or not, whereas an order ID only gets generated once the order is placed. Both these IDs acted like a tracking number in the entire order journey. Every service, let's say payment, kitchen delivery, pricing, can reference to these IDs to stay in sync. Although there are various ways to create the order and request ID, we used UUIDs or universally unique identifiers. They are very unlikely to repeat across different servers or services, and they look like the number you can see in the terminal here. Also, in our existing architecture, we relied on Prometheus to collect collect system and application metrics, and use Grafana to visualize and monitor that data through dashboards. A quick introduction to these, for those who are not aware, Prometheus is an open source monitoring system that will collect metrics from your services. It stores this data in a time series format, making it great for spotting any trends or sudden spikes. Grafana is a powerful visualization tool that connects to Prometheus and turns those raw numbers into dashboards, graphs, or any alerts. It's widely used for real-time monitoring, and it gives teams a high-level view of the system health. Together, these helped us track performance and set up basic alerts, but they had some limitations when it came to troubleshooting or understanding the full journey of a request across services. So now that we are aware of the current architecture and what an order ID and request ID are, so let's look at the core problem that we were facing. Every request and order had a unique identifier. This sounds great in theory, but in practice, not every service was consistently logging these IDs or even passing them down to downstream services. Sometimes the ID was present in the log, sometimes it wasn't. And to make matters worse, services that were in the prepayment flow were using the request ID as their source of truth, while those in the post-payment flow happened to be relying more on the order ID. There was no single consistent identifier that tied the entire order journey together. So when something went wrong, say like a payment timed out or a delivery partner was not assigned, trying to trace that failure across multiple microservices was a nightmare. This is when we realized that we had a search gap, and we couldn't reliably follow a single order or request from start to finish. At one point, the on-call engineers were in fact spending hours just debugging a single failed order. And that's just not just frustrating, it's also expensive. So we definitely needed better observability. This is when we brainstormed two possible approaches. I'll go into them one by one. Let's look at the first approach we considered. In this approach, we chose the request ID as the single source of truth for tracking a request across services. The idea was to ensure that the request ID is consistently passed through every service and logged at every step. To achieve this, we needed to audit every existing API and manually verify that it forwarded the request ID to all the downstream services. We also had to go back and update the existing logs to include the request ID wherever it was missing. So over here, we were dealing with over 50 APIs, and some of them were third-party integrations. So changing all of these interfaces meant cross-team coordination, updates to shared contracts, and a lot of communication overhead. We used the central repo as our source of truth for defining all API contracts between microservices. A sample snippet is shown in the code snippet here. So as you can imagine, introducing changes here meant careful alignment across multiple teams. Even worse, every new API or service that was added in the future would also need to manually include the request ID in this contract to avoid this problem reoccurring. And the only safeguard to this would be code reviews. So that made the approach highly error prone, and sometimes someone could easily forget to pass this ID or log it incorrectly. So in short, it was manual, fragile, and required a lot of maintenance overhead. The second approach we explored was to leverage OpenTelemetry's context propagation mechanism, or or also known as the context propagation. Instead of manually passing the request ID through every API or log line, we let the telemetry framework handle it for us automatically. The OpenTelemetry tracing works by following a single request as it travels through a system across services, APIs, databases, and any queues, and at the end, stitching that journey together to form a full picture. So when a request starts, the OpenTelemetry creates a trace ID and a route span. As the request moves from service to service, child spans are created and linked to the previous one. So OpenTelemetry automatically propagates this context, meaning trace ID and span ID travel with the request for headers in the HTTP protocol or in the metadata if you're using the gRPC protocol. So even though services are distributed, they all log and emit data tied to the same trace, allowing you to reconstruct the full request path later. We also wanted an efficient way of storing and indexing and visualizing this trace data. We wanted to monitor it in real time without many latency gaps. So this is where OpenSearch came in. With traces stored in OpenSearch, you could now have end-to-end visibility into your system's performance. You could zoom in on a specific trace and see exactly how it propagated across services. This made the debugging much more efficient and reliable since you have a single unified view of the logs, metrics, and traces all in one place. Okay, so just to quickly summarize both the approaches we discussed, the approach one would require the contract changes and also API definition changes. The second approach would only require the API definition change to receive the context that will be passed by the hotel. The first one would require changes in only the logs where the request ID is not already being logged. But the second one would require us to create a log wrapper that will help us log this context created by hotel. And and this will require changes to all the logs. The third difference is that the approach one, even though it will require less amount of changes in the logs, but will add a maintenance overhead going forward for any new APIs that will get created. Approach 2 does not have any such overhead, and no matter how many APIs you add in the future, there will be no overhead here. Because of which, coming to my last point, that approach 1 is prone to human error, and whereas approach 2 is less prone to any missing traces. Right. Okay, so we went ahead with approach 2 given these trade-offs, as it was more efficient in the long run. And even though it required adopting new logging libraries and some migration effort, I'll talk about that next. So digging into the implementation, what did it look like? Our first step was to build a context-aware logging wrapper. You can think of this as a lightweight, reusable library that could be integrated into every microservice in our architecture. We used the Zap logger here. This wrapper ensured that each log line automatically included the context, especially the trace ID, which ties logs back to their corresponding request or the order flow. Which meant developers no longer had to manually include trace information in every log statement, and the wrapper handled it by pulling context from OpenTelemetry. We also made a key shift to structured logging, switching from raw text logs to JSON formats. This made the logs easier to parse, index, and analyze them downstream. From there, Data Prepper took over. It transformed these structured logs, enriched them where needed, and forwarded them to OpenSearch, where they were indexed and made searchable in near real time. This was definitely not an overnight change, and we rolled it out incrementally, service by service, over the course of about 6 to 8 weeks. But once it was fully in place, the impact was clear. We had consistent, traceable, structured logs across the entire system. And now we completely changed how we approach debugging and observability. Once we had our trace-enriched logs flowing into OpenSearch through Data Prepper, the next step was to make the data truly actionable, and that's where OpenSearch dashboards came in. With these, we finally had the real visibility across our system. Our on-call engineers could now search for any trace ID and instantly trace its journey across more than 10 microservices, from order placement through payment, kitchen processing, and all the way to delivery assignment. This would have taken hours before, but now we could do it within minutes. And we further began by identifying the key questions our teams frequently asked during these incidents, like how many orders failed in the last hour, which service was causing the most latency, or are any certain restaurants or regions experiencing any delays, and what are the top recurring errors across our system. So we used OpenSearch dashboards to build custom visualizations on top of our logs, turning raw data into real-time interactive insights. Some of the dashboards we built include the order health dashboard, which tracked the number of orders versus those that failed in real time. The latency breakdown dashboard that showed average processing time per service using timestamps from the logs, and the error monitoring dashboard that surfaced the error messages that came across services. The delivery assignment dashboard that tracked delays in assigning any delivery partners. So these were a few of the dashboards we created, and I'll give it over to Abhay to talk about the results we observed.
Thank you. All right. So we've seen the how, we've seen the why. Now let's see what it did. So during incidents, engineers could now search by trace ID and see the full timeline across all services. This is what we planned for initially. No more guessing where things broke. Business stakeholders could also monitor real-time metrics like order rates, order fulfillment, stuff like this, which indicated how well the system and the business is functioning, helping them make quick operational decisions. And at the end, SREs and developer teams also got self-serve visibility into the microservices they owned, reducing the back and forth during incident investigations and also reducing the load on the on-call during their shift. We could set up alerts directly from the dashboards, which would help alert the on-call and any other relevant stakeholders. Now, the impact was significant and measurable. Incident debugging time dropped by a staggering 67% thanks to faster root cause identification and improved traceability. We also achieved a 25% reduction in mean time to recovery across critical on-call incidents. And most importantly, we reached full traceability for every order, enabling end-to-end visibility across all of our microservices. These weren't just engineering wins. They directly translated into better customer experiences and also more confidence in our team, our developers, our on-calls to handle any events or unexpected issues that they might run into. So, as we wrap up, here's what we've learned from this journey. Building observability isn't just about collecting data. It's about making sure that that data leads to something. It's about making sure that that data is actionable, consistent, and context-rich. Just having a bunch of logs is not going to cut it, as we saw in the beginning of this slide. By combining OpenTelemetry for standardized tracing and OpenSearch for powerful log analysis, we transformed how we debug, monitor, and understand our systems. We've moved from fragmented logs and manual effort to structured data and real-time insights, all in a way that scales with the complexity of a modern food delivery platform. Now, more importantly, the engineers received their time back, on-call shifts became less stressful, as less as they could be, and built confidence across teams. So observability isn't just a tool set, it's an investment in reliability, developer experience, and customer trust. Thank you so much for being here. We're happy to take any questions that you might have.
great presentation. Thank you. So, does somebody has some question for our speakers? Okay, here.
So you didn't say anything about sort of the visualization that you were working on. Does that mean that sort of it was the logging view in OpenSearch dashboard, which were the primary way that the developers looked at the measurements, or did you use the trace visualization in OpenSearch dashboard, or did you use any third-party other tools to sort of display the traces?
So we used OTel to collect the traces, and we used the OpenSearch dashboard to visualize these traces. And as I mentioned, we've developed multiple dashboards, and multiple teams had multiple dashboards that they could monitor to visualize these traces. There was also sort of a trace map and a service map that gets created once you set up OpenSearch dashboard. So I think that was very helpful to sort of trace the trace ID across these services.
Yeah, if you recall the graph that's like a node which connects all the services, that one is especially helpful when something breaks, in my opinion.
Great, thank you. Other questions? Okay, sorry. Lady first.
Hello, thanks for sharing. My question is, how would you map your data in OpenSearch? How would you index it?
Right. So we used the data prepper to sort of embed the data into OpenSearch. And once it was stored in OpenSearch, we used the indexing there to sort of build the dashboards.
So what trace ID might be very important in this case?
Yes,
Right.
correct.
Okay.
Other question? Yeah.
Thank you. You mentioned some limitations between Grafana and Prometheus and linking that with metrics back to the OpenSearch dashboards for logs and traces. Can you talk about some of those limitations?
Right.
What were they?
Yeah. So Prometheus is great for time series data, but for our use case here, it was very important to sort of map the traces. There are a couple of things I can talk about here. So first is that Prometheus logs were more prone to getting dropped as compared to the performance you see with OTel and OpenSearch. Most of the traces are not dropped, and you can easily trace the request across services. The second one is that with Grafana, there is some sort of latency that comes with real-time visualization, whereas with OpenSearch, it's nearly real-time, is what we observed. So that is why the shift.
Other question? No more questions. Thank you again for your
I
great.
think there's one question.
Okay.
Hi, question. So did you also log application logs in your OpenSearch? So, or was it just mainly I don't know, regular metrics?
No, so what we did was the logs, we were using Prometheus for both the metrics and the logs. The logs is what we connected with the OTel trace, and that is what we saw in the OpenSearch dashboard.
Ah, okay.
We used to see the logs in. We used to see the logs in Prometheus and use Grafana for any graphs and metric traces. That was the system we had earlier. And then later we built it all on dashboards. Right.
Okay. One more question. Here.
How big is your service system? How many nodes does it have? And how many data prepper instances were you running for this?
So service, around some 100K to 500K requests a day, but it varied across time depending on peak hours. And data prepper instances, I'm sorry, I don't have a number for you, but we had around, some services were running around 10 to 15 nodes, and the others, which were smaller, were running around on less number of nodes.
Yeah, these are service nodes, not data prepper nodes.
Yeah.
Okay, somebody has other questions?
Right.
No more questions. Thank you very much.
All right. Thank you, everyone. Thank you for attending.
Thank you.